this talk is an advances in electromagnetic solutions using the tool Altair Feko. But of course, also, as a background, this will be a two-part series, I guess. One is today, mainly focusing on Feko, which is 3D electromagnetic tool. And of course, next week around the same time, same day, Tuesday, we'll have on wave propagation solutions and applications using our companion tools called WinProp and RAD. So this is a slightly different focus, but it's all connected, I guess, in the system design of wireless systems. So today we'll do a little introduction to Altair, those people who are not aware of what is Altair about and the company itself, and then we'll talk a little bit about Altair solver technologies. And there are two topics, they have been very popular nowadays. One is the characteristic mode analysis for antenna design. Other one is the machine learning for antenna design. We'll take a look at these two and how they can be used in Feko using some of the Altair tools. And of course, we'll also look at modeling of antenna arrays in Feko. Then for those who have been using Feko for a while, like Professor John Jacks as well as Bob Pankis, we'll also talk about highlights of recent updates that we have in, and of course, what advantages or what do we provide for Altair University, that is, to universities, how do we work with the universities. So before going to introduction to Altair, I would like to show you a small video, a short video on the convergence of what we call simulation, high-performance computing, and artificial intelligence that is going through, not only through electromagnetics, but across the engineering field, and how Altair is participating in that endeavor. So enjoy this very short video, and then we'll go back to that.
The conventional wisdom says that to achieve something new, we must work within established boundaries, parameters, silos. That the size of an idea is determined by how much it pushes its limits. So what happens when there are no boundaries? What happens when the barriers separating creativity from analysis are removed? When we can refine ideas as quickly as we dream them? When insights emerge from an ever-growing sea of detail? What happens when we're no longer constrained by the limits of the physical world? We are Altair, and these are the questions that drive us. To bring together the most powerful forces in technology, across every domain of humanity, throughout every mode of industry, we enable innovative minds to advance infinitely, to change tomorrow together, to find out where innovation will take us, when instead of testing the limits, we remove them.
So I hope you enjoyed the short video. And this is to say that, we are in every field of engineering that's out there in making the products and those kind of things. Of course, Altair started as a small company back in 1985 in Troy, Michigan, and of course now grown to an international company with offices in 25 countries, and of course with more than 11,000 plus customers, and of course partner programs around 150 plus or so. In terms of the customers wise, any area of engineering you can take, in automotive, aerospace, education, energy, and all these things, you find the biggest names as Altair customers. So we are across the world, I guess, across the industry verticals with our products. The reason how, why, and we were there is because of the broad portfolio of solutions we have, starting with the design, modeling, and visualization. We're not just talking about electromagnetics here. We're talking about the complete physics simulations and design and validation type of activities across the board under multi-physics analysis as we have here. So design will be, you can think of as a 0D or 1D modeling, and then of course physics simulation is analysis, because we are also trying to combine these two things so that during the design, you can also do the physics simulation as well. Then we have offerings for machine learning and data analytics, which so we'll talk a little bit about how we apply to antenna design in the context of machine learning and data analytics. Internet of Things. This is the software that can be used to connect the physical layer, that is the your sensors and other kind of things, to the cloud. And then we have high performance cloud computing that we offer. All our software programs are available on cloud computing, so you can make use of the what we normally can call as unlimited potential of cloud computing for your simulation. So then, of course, we have Altair Partner Alliance. This is where we offer products that are not offered in our capabilities that are not offered in our portfolio. We bring in third-party tools and that are offered to the customers within our licensing ecosystem. And focusing more on the physics side, we have system simulation. This is what you can think of as 1D or 2D simulation for, let's say, system design type of things. And then manufacturing simulation. This is for the extrusions and molding and those kind of things. Electromagnetics, that's what we're going to focus today. And of course, structural analysis, as well as crash safety and blast. This is where you can also do shock type of analysis as well, and thermal analysis and fluid dynamics. And all of them can be combined in optimization product that we have, which also we'll mention briefly later on in the context of electromagnetics. So again, coming to our electromagnetic solutions that we offer. Of course, the talk is about Feko, so that's where we're going to focus. But we also have a companion program called newFASANT, which actually we acquired 2 years ago, and now becoming useful for various applications. I'll talk a little bit about that almost towards the end of my talk on what newFASANT brings to the table that we may or may not offer in Feko. But of course, eventually we would like to combine newFASANT into Feko so that users like yourself don't have to learn two tools. Then, of course, as I mentioned, next week we'll talk about the propagation software we have. So basically, you can compute the radiation patterns, for example, in a car or an aircraft and things like that, and use those computed radiation patterns as your sources in a broader environment like a city with buildings and things like that, but also in rural environment, etc., to do your virtual drive test, virtual flight test, and those kind of things. Connectivity between various systems. We'll talk more about it next week, and also we'll talk more about next week is RAP, which is a spectrum management and co-site analysis tool for broader areas. Like, you can take a province or a country and you can do the propagation analysis on those areas using RAP. Not directly connected to these products here, we have a tool called Pollux, which again, we acquired a little more than 2 years ago, a PCB analysis tool. This is where, you can bring in your, if you are into making the PCBs and fabricating them, designing and fabricating them using, let's say, Altium or Cadence and those kind of software, and you can bring them into Pollux and then do signal integrity analysis for EMI, EMC, as well as power integrity, thermal analysis, because some of them tend to get heated up, and many of the rule settings for the design electrically, but also assembly and manufacturing. So this kind of in a broader portfolio that we offer now. Of course, some of you already know that with Altair licensing system, you don't have to acquire these products separately. The units licensing system you have gives you access to all the products that we have using those units, and there is no distinction between one product versus other products as far as the licensing is concerned. Coming to the tools that we have, Feko, newFASANT, WinProp, and RAP, all of them now are available in one installation. So you don't have to install these products separately. When you install Feko installation, you already installed Feko, you already installed WinProp, newFASANT, RAP, etc. there. And also on the documentation tab, you will see various documentation available for Feko, WinProp, newFASANT, and RAP. And of course, you can click on those things to get the help menus or various manuals that we have for these products. So very, very handy in terms of usage. Coming to Altair Feko. First of all, of course, if you're not used Feko, this is just for those of you who have not used Feko before. It starts with CADFEKO, where this is the interface where you can actually create your own geometry, like I'm showing here, or you can bring in geometries from outside as a CAD models and use them in Feko. Of course, you can mesh them, and you can also set up the solution parameters, excitations, materials here. And once you run the Feko solver, in post-Feko, you can actually look at the currents and radiation patterns and fields and so on and so forth. That's, of course, very easy to use graphical interface compared to even other tools that you might have used in the past. Of course, one of the distinguishing factors of Feko is the solution technologies that we offer in one package. Typically, most of the packages come with either FEM or FTTD and so on and so forth. But unlike that, Feko offers many solution techniques in one package. For example, FEM for very highly inhomogeneous objects, FTTD similarly, finite difference time domain, metron moments, and of course, recently we also started offering ACA, adaptive cross approximation method, which can be useful when the number of unknowns are beyond your resources, computing resources. You can use the ACA, can get same accuracy as metron moments, but faster with less memory. Of course, going beyond in electrical size, you can also apply MLFMM, multi-level fast multipole method that can go to many wavelengths. I would say tens or hundreds of wavelengths based on computational resources you have, and can still solve very effectively. So all these methods here, you can consider them as full wave solutions. That means we solve Maxwell's equations accurately, and these solutions give you very accurate answers, provided you have a good CAD model and good meshing of that CAD model. Then going beyond that in terms of electrical size, one can use physical optics or ray launching geometrical optics, also known as splitting and bouncing ray method, or UTD, uniform theory of diffraction. So these can be termed as asymptotic methods. That means they also solve Maxwell's equations, but with some approximations and assumptions. So as long as you know those assumptions and approximations, and your problem fits within those assumptions and approximations, these methods also give you reasonably good answers. But of course, we also hybridize them. That means FEM works with metron moments as a bounding boundary, and also with MLFMM. So you don't have to have big airbox around your object. You can actually have it very conformal to your object. But of course, we also support the airbox with FEM. Same thing with FTTD, because metron moments hybridize with the physical optics, as well as UTD and MLFMM hybridize with physical optics as well. So this is actually a unique combination in Feko, which gives you the coupling between various methods because they're hybridized with each other. In addition to this, we have various utilities, like for example, planar Green's function. This is where you can do 2.5D problems, a numerical Green's function, large finite array analysis, which we'll talk a little bit later on, periodic boundary conditions for frequency selective surface and infinite array analysis, characteristic mode analysis, which again we touch upon this later on, and non-radiating networks. This is also important because when you have physical structures so that you model with CAD, you also want to add black boxes like your power divider or your other devices that are connected to the antenna as parameters or the SPICE network, so on and so forth, to the physical device. Of course, if you are in the EMI, EMC, and if you want to look at the cable radiations and the radiations from various types of cables because of the shielding and things like that, we have a cable analysis using multi-transmission approach. Though I won't be covering in this particular talk, because if anyone of you are interested in EMI, EMC, we can talk to you separately about it. Recently, we also introduced component library that has around 50 plus antenna templates that you can use. I'll also touch upon it in the updates section. So because of all these methods we have, you can design any type of an antenna in Feko for antenna design and also antenna placement. Because of the symbiotic techniques and hybridization we have, this is actually one of very, very strong features of Feko, and it's, I would say, industry standard for antenna placement. Electromagnetic compatibility because of the cable radiations, irradiations, as well as the shielding effectiveness. Obviously, using the techniques we have, you can compute the scattering and RCS radar cross-section, and of course, the waveguide components, as well as the radomes and human body interactions for biomedical applications. So coming to antennas, you can design any type of antenna using Feko, as I mentioned before, but having the advantage of various methods. For example, if you have wire antennas, you will have most efficient solution using, let's say, meter moments or MLFMM. Because planar antennas, you can use planar Green's function. The 2.5T are meter moments or FEM or FTTD. And arrays, again, you can use planar Green's function as well. And we have various methods how you can analyze the arrays also. Again, using asymptotic techniques, you can also analyze larger arrays, larger antennas like the reflector antennas and so on and so forth, and interactions with the human body, etc. Antenna placement in the automotive industry is widely used even for windscreen antenna design and its interactions with the car and the military vehicles as well, and trucks, etc. And of course, aerospace and naval applications as well, and other applications, radomes, with even including FSS structures in radomes, one can analyze using Feko. Of course, one of the other things is the composite structures with various orientations of the carbon fibers in the composite. One can analyze aerospace structures or any structure for that matter using these kind of technology that we have in Feko. So let's focus a little bit on a couple of the things, the characteristic mode analysis and machine learning, as well as the arrays before we go into the updates. Probably, some of you or most of you heard about characteristic mode analysis. This is something, I call this as putting physics back into simulations. In the past, when someone has to design an antenna, it's mostly either through optimization or coming up with the initial design and then going through cut and try in the simulation. Remove something and see what happens and so on and so forth. But CMA actually gives you physical insights into a structure without driving it. That means without any excitation. You can look at it and say what kind of electromagnetic modes the structure can support. And for example, you can think of them as, if you think of the waveguide, you have TE10 mode, TE20 mode, So of course, it's not same as what we're talking about here, but this is for open structures, like a wire, for example. This is the first mode, and the second mode, and third mode. And you can see the radiation patterns based on what kind of mode it is being excited. This is where, like a half sinusoid and a sinusoidal here, and a multiple sinusoidal here, your radiation pattern can change. So by knowing the mode of the wire, because wires are, we can easily calculate them, but if the structure is very arbitrary, like an aircraft, for example, you won't know the modes unless you do the calculations. So how do we design an antenna using characteristic mode analysis? First, of course, you have to get the insight into the structure. So take any arbitrary structure and check the modal resonances and currents, that is modal significance and characteristic angle and those kind of things. These are the metrics to use and where this structure is going to resonate and so on and so forth. And you select the design mode, because as we have seen before, depending on your model structure, your radiation pattern will vary, right? So you select the right mode for your radiation pattern. And then this is, of course, without exciting the structure. Then you decide how to excite it so that that particular mode is excited, and then you get the desired radiation pattern. So once you excite it, we can also compute what's called modal excitation coefficient or modal weighting coefficient. This can tell you what modes are excited in your structure, because there could be combination of modes that are excited when you excite a structure. So you want to see what are these modes and what are the weights of these modes that are excited. So once you get what you want, then of course you're good to go. If you don't get what you want, go back and adjust the excitation till you get the modes you want to get excited in the structure. So once you, of course, you excite the right modes, you verify the design and go back to the specifications, validation, and so on and so forth. So that's kind of, having the insight and being able to excite it properly, and then you should be able to do the design more with the knowledge of, physics of the structure than blindly doing the design. So as an example, let's take a simple one, because this is one of the things that we already know, an elliptical ring type of thing that we want to design as an antenna for a particular frequency. First thing what you have to do is, as we mentioned, get the insight into this structure. And if I do the modal analysis, there's a mode index that you can compute with the modal significance. So we know that when this modal significance reaches 1, that is a 2.2 gigahertz is the first mode being excited on that elliptical ring. And at 2.4 gigahertz, the second modal significance becomes 1, and that's when the second mode gets excited. So if you look at the modal currents, they look like this. For mode 1, you have maximum currents here and maximum currents here and less currents on this side. And mode 2, you have the opposite way, another flip-flop, I guess, for the modal current wise. So now looking at it, one can know that if you want to excite mode, you have a source here, and you have a source here, then you can excite mode 1. If you want to excite mode 2, you have a source here, you have a source here. So that also decides what frequency you want to excite. Let's say 2.4 gigahertz, very popular, I guess, for Wi-Fi and other kind of things. You want to make sure that this mode 2 is excited for your structure. You go and excite them at these two. And of course, look at the currents after excitation. They look similar to what we have done with modal analysis. And now if you look at the modal currents, this is of course with excitation. This is without excitation that we studied earlier. And of course, the patterns look exactly the same. Without excitation, this is the modal pattern. That is the green color. And of course, the blue color is the recreated model with this reconstruction of mode 2. And they look alike. So this is kind of a brief way of looking at the CMA design process. Of course, we have a lot of material on this one, and one of them actually is a student competition back in 2015, won by a student at University of Wisconsin-Madison on platform-mounted antennas using characteristic mode analysis. This is at a very low frequency used for this NVS communications. The whole platform becomes an antenna. You can't have an antenna big enough for that wavelength to put it on the vehicle. So the way it is done, I guess, is you take the vehicle itself and look at its modes and put an excitation that can actually make the antenna, the vehicle radiate the way you would like to radiate, that is, radiation on this side. This was actually done by Professor Nader Bahdad and one of his students. Now he's actually a professor at one of the universities in Idaho, Kingston. And they gave a webinar, I guess. If you want to learn more about this, you can click on this link and we can share these slides with you if you want to probe further on these type of applications. Also, we have written an article in Antennas and Propagation magazine back in 2015 again. If you're a member of IEEE APS, you should be able to get access to this article. And of course, if you need more information, you can contact us as well. We can provide that to you. So that's my brief introduction to characteristic mode analysis. Coming to machine learning, this is, of course, as most of you know, that has become a buzzword in every discipline, I would say, across the board, no matter where you go. So this is my one slide of my own education, also education for the attendees, I guess, is what is machine learning, right? It's a very simple analysis here of explanation here of machine learning is typically, when we go to machine learning, they call it supervised learning and unsupervised learning. Supervised learning means you collect the data that is well controlled, that you know what you're collecting. So, or maybe let me go back a little bit and say, machine learning. When you can think in your own mind that it is like curve fitting, right? You have few points on the curve, and you want like to develop a analytical expression that can represent the curve, so you can get any points on the curve without having to either do the experiment or do the simulations. So same thing with the machine learning, I guess. You collect a lot of data. Once you collect a lot of data, that data can be used for creating an analytical model that can be called as a machine learning model and can be used for further analysis of that particular problem. So in that one, the data can be supervised learning. That is, the data is very controlled, coming with known quantities. Or unsupervised learning. This is where we don't have any control over the data. It's just randomly coming in. So you have to classify the data and then form proper machine learning model. Fortunately for us, doing simulations, we can control the data. So we'll be dealing with what's called supervised learning. This can be data created by running simulations or by doing the measurements and so on and so forth. And then once the data is there, you can use the regression model to create the mathematical expression, which is the machine learning model. So to do this, we have a product called HyperStudy in our portfolio, Altair portfolio. So essentially what happens in this one is that you interface Feko with HyperStudy, which is already done. So basically you import the CADFEKO file into HyperStudy. HyperStudy imports all the variables that we defined in CADFEKO for a parametric model into HyperStudy. So you can pick and choose which parameter you would like to optimize for your gain or S parameters or whatever quantity you would like to optimize for an antenna. That part is called data collection. One good thing about HyperStudy is that we don't have to know how much data we need to collect. HyperStudy can decide based on what we call design of experiments approaches. It can collect appropriate number of data points so that you're not thinking about if I collect 10 points or 50 points or 100 points, is it good enough for the machine learning model? HyperStudy can decide and collect the data points that are required. Once the data points are collected, it can now create the mathematical model that actually can be run in a few seconds. So actually the mathematical model, you can actually have a scrolling bars and see how your relationship with goal is varying when you're varying those variables. So it's like it's a very there's no computation involved, I guess, is the analytical expression. So taking that analytical expression, you can do the optimization using genetic algorithm or any other approaches we have in HyperStudy and can optimize in few seconds. And then, of course, you can also do stochastic analysis for tolerances and those kind of things. So people ask, what is the difference between this and normally optimizing using, let's say, your own genetic algorithm and those kind of things? Difference is that if you were to do a normal traditional optimization, let's say genetic algorithm takes 1,000 iterations to converge. And each iteration, the running the Feko or any other tool takes you 5 minutes. That means 1,000 iterations means you're spending 5,000 minutes in optimizing your structure. Whereas in this case, data collection could be, let's say, 50, or let's say data collection could be 10 points. So 10 multiplied by 5 will be 50 minutes. And then once there's 50 minutes, you create the mathematical model. It doesn't take much time, and optimization will be in few seconds. So instead of 5,000 minutes, you are actually doing this in 50 minutes plus few seconds extra. So it's a very, very fast once you create a good mathematical model of your problem. So that's the advantage it brings to the table. And because of it's a mathematical model, you can run genetic algorithm if you like, or you run other optimizers as well to make sure that you are getting the right optimized model. And of course, once you get optimized model using machine learning, you can throw it at Feko to see if it's giving the right answers that you would like to get out of that optimized model. So the process will be simulations using Feko. This is a GPS antenna. We're calculating the radiation pattern there. And the data is collected by the HyperStudy from Feko, and of course, creating the machine learning model. And of course, we can create this mathematical model, and actually you can see on the fly, how these variables with a scroll bar can vary your S parameters as a response surface. Once you have the mathematical model, you can optimize the model using the mathematical model. So a very simple process, I guess, in creating this. Of course, we have offered this as a short course at 2020 APS in Montreal. And that's available now on our Altair University website at this link. Of course, as we share these slides, you can also have access to this. And this is actually a 3-hour short course that was offered. Half of it is, of course, talking about machine learning and how it can be applied for electromagnetics, and rest of the half by my colleague Gopinath Gampala on live demonstrations of how to use Feko with HyperStudy to do the machine learning. So if you are interested in this, I strongly advise you go through this short course, and it will be very, very useful for you. Again, because of our licensing model, HyperStudy is also part of your license, and you should be able to access that without any problem. Of course, you can contact us and of course RA if you need more information on this. Coming to my third topic, antenna arrays. Feko has the feature of periodic boundary conditions in both ways, I guess. You can use FEM for periodic boundary conditions, or you can use Metra moments or surface equivalence principle for periodic boundary conditions. So most of you probably, if you use any of the electromagnetic simulation tool, are familiar with the periodic boundary condition where you define a unit cell and you can compute the infinite array characteristics, but also by specifying how many elements you would like to see as a radiation pattern. So basically, we compute the single element pattern and apply the array factor to compute 10 by 10 or 20 by 20, in this case 21 by 21 array calculations. You can also specify the phase shift of these elements so you can see the scanning performance. So this approach can be the first before you go into full-blown array design to make sure that your design itself works fine, and then go for more rigorous analysis. Then we have a unique technique called DGFM. This is domain Green's function method for efficient solution of finite arrays. This is not an infinite array, so where you can take finite array, like in this case, elements like Hahn elements, for example, as long as each element is identical to the other. They can't be different type of elements, but they can be periodic, they can be arbitrarily placed. What we do is that we compress the Metra moments matrix into a diagonal matrix, so it's easy to solve in terms of memory and time and get the solution for array analysis. If you require more details, theoretical details, there's a paper published in 2014 in IEEE Antennas and Propagation on this technique, and learn more about it. So this is implemented in Feko, so you don't have to worry about the analysis of it, but you can look at you can actually make use of it, either a linear array or a circular array, but even in various planes, or a custom array. You can place them anywhere you want and can compute the array characteristics out of it. Recently, of course, other ways, take the full thing into account and compute the finite array. And we actually introduced a script in Feko called generate antenna array, where you can actually pick a single element and can choose, you want 5 by 10 by 10 elements in the array, and of course, offset of those elements. So Feko will go and create a finite array for you. And you can even specify, what type of distribution you would like to have, what kind of phase deviation or phase difference among the elements you want to have, or you can have your own custom, the amplitude distribution and can do the calculation. So first one can start with a periodic boundary condition, and once you are satisfied with your design of the array, for example, how many elements, what those kind of things, and then you can come to the finite array design and finalize your design. So this is kind of a little bit of touching on some of the aspects of Feko features, and now coming to the highlights of the updates that we have. There are many updates that came in the last 2 years, I suppose, which are I would say kind of revolutionary in a way. Some of them. One, of course, is a component library. This is where we have templates of antennas. Basically, what that means is that you have a template of an antenna without any frequency, so you can specify the frequency and we scale the antenna for that frequency of operation. And there are around 50 plus antennas right now, and also 8 platform models like this helicopter, a drone, and a ship model, a car model, as well as the aircraft models, so on and so forth. So you can use them for your analysis. If you are placing antennas onto structures and you don't have a particular model, you can use it from component library. And we'll be adding more and more as we go to newer versions of Feko as we go along. These are some of the new antennas that were introduced in the last version. You can see that wide range of antennas that are available in the component library. And other one, I won't spend a lot of time on it, but ACA, which is adaptive cross approximation, where we had this method for a very long time in Feko, almost in 6.3 version. But what changed recently is that now this is parallelized across not only on the same node, but also across the nodes on a cluster, so you can use it more efficiently if you are using it on HPC. One of the advantages of ACA is like if you're doing multiple incident angles for RCS, like monostatic RCS. As we know that metro moments is very efficient when you have multiple incident angles, because once you factorize your LU factor, your impedance matrix, every incident angle or the change of source, all you have to do is the back substitution, and it can be very fast. But in MLFMM, that can be different in the sense you have to resolve the whole equation because it goes through an iterative solution for every incident angle. ACA, on the other hand, can work like metro moment. So in some cases where you have multiple incident angles, ACA can be more cost effective in terms of the time compared to even MLFMM for multiple incident angles. And in terms of the MLFMM parallel scaling, we have, I think you can see here from 2.18.2 to 2020, we have decreased the runtime, but we also decreased the memory usage that it takes for MLFMM calculations. Of course, we also improved the parallelization of MLFMM in a large cluster up to 200. This is, of course, showing 256 processors for this problem, going from 18 hours in 2 processors to 19 minutes. So if you have access to a bigger computer, you can definitely save time of your calculations. And this is another one recently we introduced, where when we have a far field request and that is used as a source, in the past, you have to use the same frequencies that you have chosen, you have exported your far field as your sources. Now what we have done is that we have used this to interpolate between those far fields. So let's say you export this far field of this horn antenna, and it's exported to a spherical mode file. And in the other project where you are computing using the spherical mode, you can choose any frequency. It doesn't need to be the frequency that you have computed here, and Feko will interpolate between those things. So this can be very useful utility for users, I guess. Of course, we also recently introduced a link to our structural program that can compute the temperature rise of high power antennas. For example, this patch antenna, if the loss is upstairs, let's say, and you're exciting with 1 kilowatt of power, and there will be a lot of temperature and the energy loss, and that can be exported into a file and imported into OptiStruct, and you can compute the temperature rise of these ones there. So you can see, when it can be getting too hot to be used, and maybe you can make adjustments accordingly. Uh, Another one is machine learning side of it, where we made it easy to define goals in HyperStudy by actually using a post-Feko plot and exporting the PFS file, that is post-Feko session file, through a HyperStudy extraction script that you can use to import into HyperStudy and define any of the output responses as your goals. Other feature that we introduced, the new UTD solver. Some of you already know that Feko has an old UTD solver where you have to approximate the structure by plates, flat plates, and then you can apply UTD. But now we introduced what's called faceted UTD, where you can model your structure with facets, and you'll be able to compute using UTD. Some of you who know UTD very well and appreciate this fact that UTD is kind of frequency independent. Once you have the source and you have the object, and as long as you don't change the location of it, doesn't matter what frequency you do the computation, UTD takes the same amount of memory and same amount of time. This is, I call it, once you have no other option, this is the option. I know this doesn't go well, but UTD can be your option when your computer resources are out of your reach, and you would like to do an analysis to give you a good feel for what's happening in your problem. Of course, we can also combine Feko with other tools in Altair. This is actually radome analysis with wind loading using our AccuSol product, and also structural analysis. Because of the wind loading, whatever loads you have on the radome, you can do the structural analysis to make sure that it's strong enough. And the bird strike, that's impact analysis using radios. Because HyperStudy, you can combine all these things to do optimization. Similarly, you can do same thing with an antenna in open space, which is actually subjected to wind loading and other kind of things. So that's kind of, very briefly, different key features, I guess, that we introduced recently that can be useful. So I'll spend maybe a couple of minutes on the newFASANT, and then we'll take questions, if any, after this. So this is actually a software program that we acquired based in Spain. And of course, this was there around for a long time, I guess, in the 90s. I remember using a different version of this software myself before my time in Feko and other kind of things. But of course, this has been commercialized along the way and introduced various modules that can be very useful. So as I mentioned, this is part of the Feko launcher. You can go here and click on it, and this is how the front end, I guess, of the newFASANT appears. So it's organized in various modules: physical optic module, measurements module, monocross module, GTD, GTD-PO, and so on and so forth. So let me briefly explain what these modules mean. Metron moments, obviously, that of course space by itself, but one differentiator of this metron moments is that they can use characteristic basis function method. This is not characteristic mode analysis, but it's a characteristic basis function. Basically, you can think of the macro basis functions that can be applied on a large section of your CAD model rather than in a smaller triangles or in quadrilaterals and so on and so forth. Some of you who are familiar with this method, Professor Raj Mitra and the originator of this code, Professor Philip Catedra, worked together to develop this method, and it's available in newFASANT if you are interested in using it. So basically, the advantage is that it reduces, again, memory, and time. And this can be used not only with method moments, but also with MLFMM, but also with ACA methods as well. If I'm understanding correctly, you can even use it with physical optics, for example. And ModCross is a 3D RCS simulation tool. And again, here the macro basis functions that can make it possible to do very rigorous method moments analysis on electrically large structures. And physical optics, as the name suggests, this uses physical optics for error cross-section analysis. It also includes the diffraction effects if you have edges and those kind of things. Periodical structures, of course, this is the same as what we already have in Feko, but one thing I noticed is that they have in newFASANT, there is FSS primitives that you can choose. You don't have to construct, you can pick and choose. Similar to our component library, most probably will port all of them into Feko, so you'll have access to them in Feko as well. Then the GTD module, Geometrical Theory of Diffraction, it can take a direct reflected, diffracted, transmitted, creeping waves into account. Also has a MIMO module where you can compute the MIMO parameters and the Doppler effects as well. This is something, it's not in Feko, but if you want these ones, you can use newFASANT. This is a unique thing in newFASANT, that is a hybridization of GTD and the physical optics. Again, they take into account diffracted fields as well as creeping waves into account by doing this. So there are two different things that I don't think in Feko we have, but probably in WinProp we have parabolic equation either in WinProp or in RAP. This is a propagation equation that is used for longer distances and things like that. If you need it, you can use it, but also alternatively you can use in WinProp or RAP as well. The last one, the ultrasound module, that is something again unique. I don't think we have anywhere in the Altair portfolio where you can model the ultrasound emitting sources. This is ultrasound, as the name suggests, is a sound wave. So instead of solving Maxwell's equations, you can solve the sound wave equations, which are scalar in nature, and we can compute near field coupling, Doppler effects, and so on and so forth. I was told that this is widely used in automotive industry as parking sensors. So I wouldn't be surprised if your car has these sensors and have been designed using one of these tools. So that's of course about my technical presentation. And for students, we have a free student edition that you can download from altairuniversity.com/Feko student edition. That includes both Feko for antenna analysis, but also propagation analysis as well. We have free eBooks, both for Feko and WinProp. This is where you have video tutorials and other things. You can click on a link and go to a video tutorial, so you can learn Feko very quickly using this ebook, and could be useful in the classroom as well. Last one I want to mention is the textbook that we have. I co-authored with Professor Elster Bainey and Professor Payam Nairi at Colorado School of Mines. This is actually an antenna book. I call it antenna book without equations. So if you're curious about antennas but don't want to learn all the math, which I don't suggest for the students, but this can be one way to learn antennas if you're a practicing engineer and you don't want to go through the rigorous of the ones. But also this could be a good a way of learning or making interesting introduction of antennas to, let's say, undergraduate students who are sometimes turned away from electromagnetics because of equations, but this could get them the interest going. Then the equations can follow subsequently. So, of course, we finished our first talk now. Just a reminder about the second talk next week. And of course, any questions, myself and my colleague Ray can be contacted.